That is also is going to be built. I don't know if they are built yet. And I said China also has one. So, hello. One of the things that one of you mentioned is that how they control this. Yeah, how they control is magnetic levitation. The train is on the air. So how do you control that to go on the rail? So there is one system that is called electrodynamic system. We have electromagnetic system or electrostatic system. This is electrodynamic system. It's so that you have this kind of conductive paths on the rail. Yeah, the rail is made of conductive material. Yeah. Now, on the rail, they have paths of, for example, copper. Just like that. Just like that. And then you have a big magnet. The magnets are superconducting. Who remembers why? Why the magnets have to be superconductor? Yes. Why not? Why don't they use copper? Why do they use superconductor for coil? We said that. This is, for example, a magnet of a few Tesla. And if you want to have a few Tesla coil with a copper coil, so you have to have a big generator, power supplies, just to continuously give this power to these coils. And this is not possible on the train. It's not economical. So they make it superconductor, and this superconductor, they just needed to charge it once. It's like MRI system. The first time that they want to charge up MRI coils, it takes days. A couple of days. It takes some time till they charge it up. They increase the current, and then there is a high energy there. Yes. By the way, this when you have a superconducting coil full of energy, means that you have such a thing to say. So the energy inside this, and if it is 1,000, even 1,000 amps, then this is something like 10 hundredths, and it's more. Then you have 10 megawatt energy stored here. If anything goes wrong, it will be a bomb. It will be like a bomb. Because, for example, if this is one part of it is lossy, becomes lossy, one part, for any reason, then that part generates heat. That heat makes the superconductor weaker, and again becomes weaker, the resistance goes up, the heat goes up, and then at one point, then it becomes normal. Then when it is normal, you have thousands of amps going to a resistor, a few ohms. It starts to melt from there, and the whole energy will be emptied. At that point, everything explodes. Because this is, for example, most of the MRI systems that you have use liquid helium. Yeah? Liquid helium, what is the temperature of liquid helium? 4 Kelvin. Yeah? It's about 4 Kelvin. Now, you have a big amount of helium, 4 Kelvin, and you have 10 megajoule energy. Wow. It's a bomb. And the whole building goes down. Yeah? This, what I explained, it is called quench process. Okay? quench process, and it is a very dangerous process, and there are many safeguards, fuses, control systems to protect that and not let that happen. And there are some resistors shunted with that until as soon as it happens, the energy goes to the big resistors outside and empty the power, dissipate the power. So let's go back. So the coils are superconductors, okay? So they work like a permanent magnet. So you don't need any more energy, you just need to keep them warm. Yeah? Then when they move, when you have two coils like this and one magnet here, what will happen when it moves? If you move here, yeah, if you have two coils like this and you have a magnet, let's say just this is your magnet, N, S, doesn't matter. You have a magnetic field. When it wants to move, it goes in the middle, not here, not here. Why? The coil, the magnet when it moves, keeps itself almost in the middle. Why? It doesn't go from the loops. It doesn't like to go over loops. The magnet doesn't like to go over loops. It wants to go in between the loops. Why? It is just physics, electrical physics, electrophysics.
Because we need to maximum of magnetic field.
To need, it is very simple, don't complicate it. What you said? You want to say it, repeat it, or?
Maximum of magnetic field.
You have the magnetic field. The magnetic field is constant, and it is, for example, 2 Tesla, 3 Tesla. When I want to move it in between the coil, from the coils, it doesn't like to go through the coils. It likes to go in between. Why? Let me help. The Lenz's law, Faraday's law, Lenz's law. If I have a loop, then if I have a magnetic field over that, what will I have? I will have dP over dt. Yeah. Then it generates current, and that current generates magnetic field opposing my magnet and pushes the magnet away. If you have a ring, and if you want to pass a magnet over it, it pushes it away. Because when the magnetic field comes through this, you will gonna have dP over dt, and then it creates a magnetic field opposing that. Yeah? It generates magnetic field, opposing that. So the magnet will be pushed away. The magnet will be pushed away. Clear, guys? If I have this as a magnet, I want to do this. This pushes this here or here. Doesn't let it to go through here. Okay? So, when the magnet moves and you have such a structure on the wall, it's clear what happens. When it moves, it pushes the magnet to go high and goes from the middle. And also you can have magnets here. So then you need a repulsive force for this, and it can have a turbine, like a turbojet, like an airplane, yeah, like a hovercraft. You know hovercraft, yes? and it works and just moves it. When it moves it, it gets levitated. And from the sides, distance. At the one, it's like that you have made it, fix it to go between these guys. Yes? So, this is called, the system called, is called electrodynamic system, and mostly this is used. Mostly this is used. And, okay, and this is what I mentioned yesterday, that here, when you have high edge in a ferromagnetic material, most of them, they get saturated about 1.5, 1.6, maximum 1.7 Tesla. And then it saturates. Yeah? This point is about 1.7. And after that, if you want to go higher B, you have to have much higher H. Yeah? And H is proportional to I. What this means? It means that when I am here, I need, for example, 100 amps. I get 1.5 Tesla, for example. And if I want 2 Tesla, so I have to apply like 2,000 amps just to get 0.3 Tesla more. If I want 3 Tesla, oops, did I go that far? Yes. And if I want to get 3 Tesla, okay, you need tens of thousands of amps. It's not going to work. So you cannot have a magnet of 3 Tesla using copper coils and ferromagnets. It's just not possible. Only superconductors can do it. So if you go to MRI, actually for my back, I did a lot of MRI, guys. Because of my backbone, I have problems. And, well, I have real problems, guys. One of my, I don't know the name in English, these pieces. You have your spinal cord, you have bones that, like discs and things. What do you call those bones?
Discs.
Disc is what is in between the bones. But the bones itself.
We call it позвонок.
What?
Позвонок.
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 Позвонок. Okay. Позвонок. Yeah. These poзвоноks that I have, 3 of them are like this. And 1 of them is like this. And 2 discs are gone. That's why I am doing this. 3 months ago, I was in bed for 22 days. Just in bed. And I have just started to move. Actually, I should have a surgery. I don't like it. Because they want to put screws and nuts and do all of these. And 5 of them, they want to screw it. I said, okay, forget it. I'm not going to do that. You know, it's very dangerous. When you screw them, if anything happens, whoa, the spinal cord will be gone. This is more easier. I will handle it. You will see. You will see. So, why did we get there? Because of MRI. And these MRI systems, when they are over 1.5 Tesla, they're all superconductors. They all are superconductors. Anyway, they are various systems. Yeah? And even they make systems that they use these inductions in the side to move the train even. I don't get into details of it because it's kind of engineering system. But just know that also you can have electromagnetic suspension. The rail can be like this, and it's a ferromagnet. Then you have 1 superconducting coil, 1 superconducting coil, 1 superconducting coil, and 1 superconducting coil. Now, these 2 tries to keep them here. these two tries to keep them here. So these two lifts it, but then you know it is not stable. It may stick here or it may stick there. Yeah? It can stick here or there. Then they put these two, not to let that go left and right. So the side ones lift it. This middle ones doesn't let it go left and right. But the other one, electrodynamic, is more popular than this electromagnetic suspension. Okay, and these are much more advanced. That they use the coils in the side not only to balance it, also to move it instead of turbines and jets, turbojets. Yeah. Okay. These are the things I wanted you to see. Yesterday we talked about the resistance, and here you have only super electrons. Here you have two fluid model, two fluid of electrons, normal electrons, super electrons, and then here you have only normal electrons. Yeah, you have normal electrons here. This is superconductor, a mixture of super electron, normal electron, and at this temperature, you only have super electrons. Yeah, this is what we discussed yesterday. By the way, I prepared the 1.5 to give it to you for these things. I talked to Professor Vera, and she said that she can distribute it to you, but I can also give it to you. And I don't know how would you copy that? I don't know. I can have it, on a flash and give it to you. But how should I do that? Should I give it to Professor Vera to send it to you all, or
Yeah, maybe.
is it easier? Okay. So then we said that we can model. We said that we can model the superconducting material like a inductor and like a resistor. Yes, and inductor part is kinetic inductance. Is due to the kinetic inductance of the electrons. Yeah, we said electrons have mass. So when you apply electric field, it takes time for them to move. There is a mass, so they cannot get accelerated quickly. So it takes time. So there is a lag. We talked about lag and lead. You remember? And we had this analogy as example with a plate and a ball. Yes? We said that when you do this, it starts to accelerate like this, and then when you do this, still it may go that way because of the momentum, and then goes that way, and then it starts to come down, and when you do this, then there is a phase difference between what you do and the velocity, and that phase difference is how much? If it is pure inductive. Do you remember the phase difference between this is electric field is equivalent to potential? Yeah. The slope of the plate is like a potential. It's like electric field. The motion of the ball is like what? If the plate, the slope of the plate is voltage, like voltage, electric field, then the motion of the ball is what? Velocity, current. Now, then this velocity or the current with respect to the slope equivalent to voltage, it has a lag or lead. It is behind or ahead.
It has lag.
It has lag. It has lag. And how much phase difference do you have if I do this? How much phase difference do you have? Because this is kind of AC, And the motion of the ball is kind of AC, back and forth, yes? So it's like that. Your voltage is changing, your current is changing, but the current has a lag compared to the voltage. How much is that lag?
Pi divided by 2.
The lag of inductors, the current and voltage. It is 90 degree. Yeah. If this is
Pi divided by 2.
pi divided by 4.
4. Yeah.
Not correct. If this is the voltage, yeah, then the current is which way? Shift. Which way? Should I start from here, here, here? If I start here, it's in
The
phase.
maximum is
Current is later.
when
Later. Very good. This would be the I.
Yeah.
So actually, when the slope is maximum, it may cross 0 because just, for example, moves. Even the transient, if considered transient. And then, when the slope is 0, it has its maximum velocity. Because it has been like this. The ball has been going fast, yes? And it is going faster and faster and faster. It speeds up. Yeah? And then, when it has an acceleration. When you have it like this, it means that you don't have voltage, you don't have a slope. It has its maximum velocity going that way. Then you apply reverse voltage, reverse slope. That is going that way now. It slows down, and then comes back. Yeah, it has a lag. So, this inductive parameter, it is only the characteristics of superconductor and the superconductor fluid. The superconducting part doesn't have any R. Now, normal electrons also have mass. Yes? So, they also contribute to this model as an inductive part. Yeah? So, let's do some formulation. Okay? For this two fluid model. Let's do some formulation. This is the general average velocity in the x direction differential equation. You have m dv over dt, yeah, plus m v sub x over tau equal to minus E times E electric field, which is equivalent to potential. This is equivalent to current. Is the velocity of electrons. Yes? So, velocity of electrons means current, potential, electric field is the voltage we apply to the material. So, this is the general part. Okay? Now, term 1 is due to the acceleration of electrons, the energy that it gets to get, accelerated. And the term 2 is due to the collision of electrons. So this part is lossy. This part is lossy. This part, no, is not lossy. This part is lossy. This part is not lossy. So this is the inductive kind of part, and this is kind of resistive part. This is the general equation for electron velocity. Yeah? Now, if the changes in electric field is slow, which means this is a slow, the variation of that is slow, then V sub x becomes E tau over M times Ax. It's like a DC. I is equal something times V. Sigma times E. Yeah? Is the Ohm's law. Is the Ohm's law. So whenever you see V, look at it as I. Oh, it became interesting. Whenever you see V, look at it as I. It means that we are I. All of us is one. No, that's not possible. It doesn't work. Yes? We and I. No, we is many people, I is just one person. Okay, anyway. When we have you look at this guy, means current, not I. So, and this is the voltage, and this becomes sigma. Now, if you consider the electric field variations as e to the power j omega t tau, okay, means an AC electric field or AC voltage, let's say. When you have E in this form, and then this of x, based on that equation, if you solve it, will be like this. Yeah, in simple differential equation. Solution to the simple equation. So, now, J is equal minus N EV. So, if I apply NE to this V, I get this, and just the J, I bring it to the denominator. Yes? Now, this will be the form of the current. Now, for a slow varying field, we said we have this. And we know that V or I is equivalent to sigma times V or E. So this is sigma. Okay? This is the conductivity. Conductivity of a material. That definitely depends on the number of electrons. If you have more electrons, the material is more conductive. And M, the mass of electrons, if it is lighter, okay, you can have more current for an electric field. Electrons move easier, faster. If it is heavier, now sigma goes down. Tau, what was tau? Tau, the mean free time between collisions. So you know that electrons hit constantly, yeah? You remember ping pong we played? Yeah. The mean free time is the time between this, the average time between these kickings. You don't have ping pong around? Ping pong?
No, not now.
Maybe on computers.
On campus?
Computers.
On computers.
On computers? No, on real ones.
No,
Real ones
we don't have.
Do you play also this thing? The football?
and soccer.
The football?
I understand.
Sometimes.
Where is it?
It's not here.
No.
It's outside of the university.
It's like in center, in gaming centers with.
Who want to compete with me?
I've never played it.
I'm a good player. And I can do like a penalty things. You do that, shooting. You put it and then you look which angle is empty and then you from beginning to the, yeah?
You have really good skills.
Yes. I can play. I can play well. I still can play. Yeah, I am a good player. And I am not those guys that just rotates things, yeah? You know, you have seen some kids, it just keeps rotating. And it works. And many times it works. And it gets on your nerve, you know? You want to play and the guy does this. Come on, I want to play. Okay. So, this is the mean free time, it is the average time between two collisions. Yeah? We said that we have this collision for the electrons. So, of course, if tau goes to infinite, what does that mean? If tau goes to infinite,
No collisions.
no collisions. So,
Sigma goes to
infinite. Why? Because if there is no collision, you have electric field, the electron can get accelerated to the infinite velocity. Yeah? They can just, it is like that, you have a plate and you have a ball and the plate is infinitely long and you release the ball. If you don't have friction, the speed just goes up and up and up and up and up. Yeah? You know, this is ballistic missiles. The ballistic missiles, they're dangerous, you know, they cannot handle that. Because when it goes up, and from the very, very high altitude, then it just comes down. And it gets damn high velocity. And no other missile or nothing can hit it. So it comes so fast, you know. You can't hit it by anything. The velocity is enormously high. And that's why ballistic missiles is a big problem. Now you need very, very, very complicated system to hit it. You should be able to see it much earlier. Yeah? You should be able to see that missile much earlier till you can fire something to get it on the way of it. You cannot follow it. It's too fast. So you have to get, you know, on the way of it. Okay, good. You know, I had a Pakistani PhD student, and he wanted to go to England to see his brother. This belongs to 20 years ago. And then his name was Rizwan. And at the embassy, British embassy, they were delaying his visa, and he had got annoyed that why do you delay my visa so much? And the guy say, hey, you are engineers. You can do hell of the things. We have to be careful with you. Because you can, with the engineering, you know, with knowing physics, there are lots of things that you can do. Very easy, you know. Should I teach it to you? No, I don't teach it.
You may.
No way. No, you can easily make things, you know, that is very dangerous. Just fundamental physics. Just one inductor, I told you. You can give a shock to a guy. Easily, with a battery and some, you know, some wires. You can give a shock to guy. To paralyze the guy. So when tau goes to infinite, then sigma becomes infinite, and what you will be left will be the acceleration part. Yeah? You will be left with the acceleration part. And when you have electric field, the velocity keeps increasing. Yeah? If this is constant, then it means that you have acceleration. And V is constantly increasing. If it is AC, then this would be AC. Overall, it would be imaginary part. It's like inductor. It's like the inductor. You have 90-degree phase shift, and it is not lossy. So then for the current, you have sigma Ex, then you have minus NEV, J sub X, then becomes minus J NE to the power 2 omega sub Me, pure imaginary, pure inductive, no resistance. A perfect conductor is inductive or capacitive and resistanceless. So we are talking about it as a perfect conductor. Now, the superconductor, actually we are looking at it as a perfect conductor. Fine. And here we further emphasize that this is for perfect conductor in 0 Kelvin without any defects and with an approximately infinite mean free path, mean free time. Both are correct, yes? Mean free path is corresponding to mean free time. The distance that you don't have the collision or the time that you don't have the collision. They are kind of parallel, yes? Good. Now I can model the conductivity in my material. I can have superelectron part contribution, which is pure inductive, and normal electron. Now this time I added this part because normal electrons also have mass. Normal electrons also have mass. It's not that they can move quickly. They are heavy also, and they create lag. So for normal electrons, we have both their lossy part and inductive part. And let me tell you, in microwave high frequencies, this part, we don't have superconductors here, yes? But in their calculations, it is normally copper, silver, gold, whatever. And in the calculation, they do consider this. Because at very high frequencies, then this shows up. Even for normal conductors. In cavities, microwave devices, this inductive part comes up. So, this background here, it is looking, mine is better. Here, the color is a little gray, but here is green. So I look at it here, it's easier for me. I don't know about you. So, okay, the PDF will be good. It's like this. It's not like this. So, superconductors. For the superconductor, we have n prime d v sub s over dt equal minus e prime times e, and this means superconductor. M of super electron, E, the charge of super electron. Yeah, this is 2e, and this is 2m almost. So this is what we are saying. This is E prime is the same as E asterisk. We say 2, and this is 2. And for the normal conductor, we have both components: the inductive part, the lossy part. Inductive part, lossy part. So we have both components equal to this, and J sub s, which means the current due to superelectrons. The current due to superelectrons is minus n sub s prime e prime v sub s, and the current due to normal electrons, again the same thing. So this is the, also I mentioned that this is the border between continuous path of super electrons and non-continuous super. You know what I mean? When you are here, you have lots of normal electrons, but the resistance is still 0 because you have continuous path of super electrons. Yeah? When you reach here, you still have lots of super electrons, but you do not have continuous path of super electrons. Then you will have losses, resistances. Because in some parts, the current has to be carried only by the normal electrons, then gets to the super part, electron part. So then it starts to get more and more till here, you don't have super electrons at all. Then it will behave like a normal. So it's not that super electrons vanish instantaneously. They vanish gradually, or they form gradually. Yeah? They form gradually. So, now, the total current then will be the sum of both currents, super electrons and normal electrons. Yeah? So, then I can define a conductivity with two components. One component real part, one component imaginary part. Yeah, I can define that. Now my sigma would be a complex number, and then in normal, sigma becomes n e to the power 2 tau over m, sigma sub n, then would be in this form. And then I can get this imaginary part off from the denominator. Then I can transform this into this and this. Yes? We have done this many times. So this would be my sigma n, sigma sub n. And then in superconductor, I have this. Tau goes to infinite. Then I will be left with only this part, an inductive part. Yeah? Then, okay, superconductor has only the imaginary part, normal conductor part, normal electrons create both real and imaginary part. Then my sigma 1 will be equivalent to this. My sigma 2, sigma sub 2, will be equivalent of summation of this and this, which is this. Yeah? Okay. So now I have the complete model, sigma sub 1, sigma sub 2, and now for the total J, I can write it in the form. So, with increasing the frequency, the resistance will increase, but we still have superconductor. On the other hand, we increase frequency high enough, we give super electrons sufficient energy to become normal. What does that mean? When you have too high frequency, when you go to very too high frequency, it's like that you are reaching the photons, yeah? Too high frequencies. When you go too high frequencies, the energy that you are applying to the material is high enough to break pairs. It's not that you can increase frequency as much as you want. After some frequencies, the energy of radiation that you are giving is more than the energy of binding, pairing. So they break. In semiconductor, it's like what? In semiconductors, it's like in semiconductor, when you put photons with high energy, what happens? In semiconductor material, when you radiate the silicon with high energy photon, germanium, whatever.
The electrons go through.
Exactly.
They overcome the forbidden gap.
Exactly.
They go to the
Conduction.
Conduction.
Exactly. Then you get electrons in the conduction bands and holes in the valence band.
Yeah.
Here, same, if you go to very high energy, then pairs break. They go to the normal state. Okay? The same thing happens here. So, for low enough frequencies, but this is still low, 100 gigahertz, where omega to the power 2 times tau to the power 2 is less than 1, and using, this is the Planck frequency, and using lambda sub L, the London penetration depth, that we will work on it, we will show it, the sigma sub effective becomes sigma sub 1 minus j sigma sub 2, almost becomes sigma sub n sub n over n minus j times 1 over omega mu sub 0 lambda to the power 2, and sigma sub n, it is n e to the power 2 tau over n. These are just replacing the values, okay? Just replace. Sometimes I give these as homeworks. Where is your homework? Yeah? Okay, so just, you can give it to me. Don't forget to give it to me, okay? And don't forget to have your name on it.
In the break?
Yeah, in the break. You can just leave it on this desk. Very good. So, you are the same. Students are the same everywhere in the world. When they have the homework, something that they have to hand in, they don't say anything. And if I don't say, they just go. They don't hand in. And even those who have done, they don't dare to say it. Yes? Some people have done it, some people have not done it. Those who have done, they don't say it. Because those who have not done, then why did you say it? You have the same thing?
Yeah.
Yeah, the same, good. Less work, easier life, yes? By the way, on Monday you're supposed to have a quiz.
Yes.
Yes? Ready? Yeah. These professors, they don't let you have fun. So, sigma is in the normal state and n is the total electron density. Therefore, temperature effect and n, now n's that we have, also in lambda, n sub s that we have, now here we can apply the n's as a function of t. So actually, this equation is a function of t. Yeah? This is a function of t. So your sigma changes versus temperature. So what it means is here. Now, who can explain this? Who can explain this? Why yours is closed, mine is open? This is not fair. You open that I close. You get cold?
Yeah? No.
It's okay? And you? It's okay? I am a guy who is sensitive to cold. Some people are sensitive to cold and some people are sensitive to heat. Yeah? Oh. Well, he is a hot guy. Will you be okay?
Okay.
How about you?
Okay.
You're fine?
And you?
Did you have a drink something before you come to class? Maybe lots of chocolate.
No.
It's always like that? Well, you are in St. Petersburg. Fine, I know. I was telling Vera that it's a little cold, and she said, no, it's a lovely warm weather.
Yeah, it's okay. No,
See?
it's not that cold yet.
It's not cold yet. I am not a cold weather guy, Well, I have to keep eating chocolate. If I just, keep eating chocolate, then I remain warm. For example, when I drink with a, no drink, not that drink, I mean drink, sweet drink. With a little chocolate, I sweat. Quickly I sweat, in a minute. I sweat, and then I get warm, and then after 10 minutes, I get cold again, it's gone. So I have to constantly eat chocolate to remain warm. And this is bad. But that's why I don't get fat. You know, the metabolism, do you know metabolism?
Of course.
You say the same thing in Russian?
Yes, yes.
Yeah, it's damn too fast. It's not good at all. It's not good at all. If I don't eat something for 3 hours, I get headache. My blood sugar comes down. Of course, if I sleep, doesn't matter. When I am working, forget it. 2 hours is maximum. I have to eat something. I do have. Now, you have been thinking about this during this time or no? You were listening to me.
Both.
Both. Good. Someone explains this. And I'm not going to continue before you explain this. What's happening? All these equations and variations in the conductivity, which is in the all materials, yeah? You can have the kind of various conductivity in various materials, semiconductor, superconductor. The principle is the same, yeah? Of course, in superconductor is more beautiful because it's more complex. So, who can explain? No?
This shaded line means that complex conductivity does not exist in normal
Or
state.
it is a little. It exists.
Little.
Anomaly.
This much. Here is normal state. You don't have super electrons. Here you have mixture. Normal electrons and super electrons. Now, okay. Sigma sub n 1. Sigma sub n 2. Let me remind you.
I think sigma 1 is the end
See here, let me bring it. Here it is. Sigma 1, Sigma 2. Was it the noise or
Noise. Noise.
not cold?
Not cold. Just noise.
You don't want to confess that you got cold. You don't want to accept that you got cold. Yes. Okay. Okay. Hey, I forgot to write when. Yeah. Okay. Because you did that, I remember that I had done that. So, you know, whatever you fixed, again, when you could get to the school, you put it away and the whole thing is gone. Sigma sub 1 and sigma sub 2. Yeah? Okay. Now,
Sigma 2 kind of reminds about the picture in first lecture, like three dimensions.
I can't hear. Very good. Go ahead, go ahead.
And not like that curve when temperature, electric field, magnetic field.
When the temperature here goes up, yes? For example, if here is 10 Kelvin, here is 5 Kelvin, here is 20 Kelvin, for example. Now, when the temperature increases, sigma sub 2 decreases.
Yeah, it goes
Why?
off the state of superconductivity.
I didn't hear.
Goes off the state of superconductivity.
Yes. So what do you lose here? I mean, what causes here? You go out of superconductivity.
We lose.
Yes. This is the part due to which kind of electrons?
We lose super electrons.
Super electrons.
You're right, but I want to get to the electrons, not the state of superconductivity.
Okay, I just not was yesterday. So
I see. So this is because super electrons go down, yes, and the effect of super electron goes down, but still you have a little inductive part. Why? This is clear. This is due to which electrons?
Normal.
Normal electrons. And normal electrons are lossy. Okay. When you go to 0 Kelvin, normal electrons vanish. You don't have any more normal electrons. If you don't have normal electrons anymore, then you don't have losses. The sigma, lossless sigma is gone.
But conductivity low.
Yes, the conductivity due to normal resistors go away, becomes 0. So there is no loss. We have only conductivity due to super electrons, which is imaginary part. Yes?
Yes.
Now, when you go from 0 Kelvin to high temperatures, super electrons become less and less, but still you have some. Why? The normal electrons increase, these super electrons become normal electrons, so that lowers this increase. Fine, then you have a constant number of normal electrons. So even if you heat it up, it's the same, yeah? And the only effect that it can have, it can be due to tau, military time, due to
Maybe
temperature.
in this state, normal electrons work like super electrons a little bit.
Why? I am saying sigma 2. I am not saying super electrons only. Sigma 2,
Just conductance. Yes.
yeah,
This region. The mass of electrons.
excellent. The mass of electrons, sigma 2, where are you? Here. It has one part due to n sub s, number of super electrons, but it also has a part due to normal electrons, n sub n. Yeah? Normal electrons also have mass, and they have inductive parts. They also have mass. This goes away, that remains there. That remains there and doesn't go to 0. Good. Let me see. I should consider. You were the first time saying your name?
yes, you did.
Which number?
8.
8. Nikita? No. Oh, Nikita. Oh, was the same name that I said is more for the girls or no?
Yeah.
Yeah.
Okay.
Brain memory is super good.
Yes, Nikita. And Amamo. Who else contributed to this analysis? Who? No? Only Amamo? You also did some contribution? Or no?
Oh, where?
No, for this analysis. I wanna give
Previous.
I wanna give pluses.
I
I-
don't know. I don't think I said something that important.
Important. So for Nikita and Amamo, you got a half plus. The guys, these pluses, I count on them, so be active. Did you say also something or no?
Yes, but it wasn't so
No?
important.
Okay, so you're a good judge. I trust you yourself. Okay. Good. Now, for the penetration depth, Last time we had this, yes? We explained this. And the lambda penetration depth, we also explained this. Now, let's look a little more into this penetration depth, okay? Let's look more into the penetration depth. We had this, we discussed that, in general for electrons. And we had this, tau goes to infinite, then we get this. And E is proportional to variations of J over T when the tau goes to infinite. When tau goes to infinite, then if you have electric field, you will have change of current. When tau goes to infinite. So, in a superconductor, when you have E, which means you have potentials, yes? V is equal integral of E dt, yes? Now, when you have E, you have variations or change or increase or decrease of current. When E is 0, J is what? No variation, no, nothing. Constant. So, that's why in a coil, a superconducting coil, or in a superconducting circuit of a ring, you can have current, no voltage. Yeah? Because if you have a voltage, voltage times current means power. And if you have a ring, and if you have induced current, yeah, then you don't have any voltage. You don't have losses. You know, it's like this, that electrons have been accelerated and they don't have a collision, so they keep going, they keep going, they keep going. Yeah? It's like that. When you accelerate the electrons, it's like a ball that you put it in the ring and push it. If there is no friction, it keeps going without any force. Okay? Now, so we understand this. This we know that curl of H equals J. By the way, magnetic field, what happened? Did you think about it? Why a charge, when the charge moves, create magnetic field? That big question.
It's related to the spin.
No.
Magnet is the direction of
The spin?
the.
No, you are thinking too complicated. It's too complicated what you're thinking. No, it can be answered simpler because that I am not sure if you can get to a result. If you go that way of analysis. Nobody else thought about it? Hey, where is this guy? Vasily? Sleeping?
Sleeping.
Maybe.
He's sleeping. He's just late for
Yeah?
2 hours.
Oh. Oh, okay. He will arrive.
Yes.
I think he's gonna having now a nice, beautiful, delicious breakfast. And I was eating like this, tap tap tap. Looking at this. Yeah.
I think he have nice, beautiful sleep.
And
Yeah. Very nice sleep and then very nice breakfast, relax, coming to. Hey, I'm jealous.
I think after that morning he could answer a lot of questions.
Well, he missed that. Okay, I teach a lot. Just to make compensate, you know. I'm jealous that he could sleep very well, he could have a good breakfast, and I could not have any of them. So, well, when he comes, actually he should buy something for everybody maybe. To compensate, yes? Sometimes back home I do that. But not because of being late. for different events, and then sometimes students buy ice cream for everybody, or I tell them that don't come in without a box of sweets. So they come with the sweet. The whole so anyway, the curl of magnetic field is equal to J. Yeah? You know these things. Yes?
Yes.
You know? And the curl of H dot bar means the round of H to round of from is the value. Would be m e to the power 2 over m times e. So, now, in a superconductor, if you have electric field, there is a change in the current. We said that. If the current is constant, that is, we do not have electric field. Okay? Good. Now, in superconductor, we don't have this part. You know this equation. We don't have this part. This is the charge continuity equation. Yes? And then we don't have accumulation of charges under steady state. So we don't have this part. So then the curl of H dot bar would be J. In a superconductor, we do not have accumulated electric charge. We cannot. In normal conductors, it may happen. In semiconductors, it can happen. In superconductor, it cannot happen. Why? This is a big thing.
There are no electric fields.
No, assume that momentarily, if you have electric field, you cannot have this. Why? Cannot have this. Oh, also, Gleb is not here.
Yes.
He's sick.
Oh, Corona?
No, I think something. He's not feeling well.
I think Vasily and Gleb has made a team.
Maybe we have breakfast together.
Maybe. Well, it means that last night they have been in a party.
Probably we sleep together.
Yeah, maybe. After the party, of course.
Of course.
So they have team up. So who can answer this? Who can answer this? Why the guy, you are saying these things so clearly, very strongly. You cannot have accumulation of the charge in superconductor. Why? You know why I remembered Vasily? Because the discussions that we had yesterday about wave functions, bosons, bosonic and fermionic things, and the superconductors, they have all one wave function. And he said that why we can have the same, so if wave functions, so they are bosons. I said no, there's still fermions. They behave like for bosons. And then we got to the point, he tried to understand how this is possible, and then the answer is the answer to this.
Correlation?
They are correlated, but then how they can have the same wave function? They are fermions. Pauli exclusion principle doesn't let that. So
Okay.
why? Why super electrons, they all can have the same wave function? Yesterday we talked about it.
Coherency. So many.
They are coherent definitely, but even if they are coherent, Can we have two electrons with the same function, wave function at the same position? Can we have two super electrons, two pairs with the same wave function at the same position? No, they are not at the same position. It's like that, I said. It's like that. Two people are dancing. Yeah. And then they're dancing. Yeah. And then there is another guy. There's another guy. Another couple. Why he has his head like this? Okay, let me also then he's looking at this. Okay, good. This guy can look a bit here too. They're looking for each other. Now, this is dancing and this is dancing. They have the same distance, they have the same speed of rotation and anything. This is possible that they dance on a circle both together. How? The only way it's possible, one of them be here, one of them be here. If this is couple 1 and one of them here, one of them here, couple 2. Now they can have the same place, rotating, the same dance, yeah? But this, if I put it like this, now they can dance without hitting each other. They are a little apart. Yes? They're a little apart. And they are all coherent. They're all coherent. So many couples can dance without hitting each other. So if I want to have this accumulation, what does that mean? It means that you have more super electrons at one position. That cannot happen. They hit each other. They are not allowed to. They can't. Pauli exclusion principle doesn't allow that. They have to remain they have to be distributed the way that they can have this dance. Yeah. I think they're more beautiful than this. Yeah, they're not that beautiful. Those couples are. You like dancing?
No.
No?
In darkness. We are boring physicists.
Well, the nice word for that is nerds.
Yes.
Well, dancing is good. It's a good exercise. Maybe. It seems that you have not danced in your life at all.
I'm never tried.
Oh boy. Now you see why you're a boring physicist. No, dancing is good. It's exercise.
Let's try.
Let's try. Do you want me to do this? Actually, Russians have this dancing with the feet.
What?
They do this. No, I cannot do it. But with these dancings, they go around like this. Kazakhstan. Yeah, there is a dancing. They-
Яблочко.
They wear black things with it's like a skirt kind of thing for the man, and here is clothes, and then they have hats like this. What is that? Papa? Papaka?
It's not actually like Russian national
Caucasian.
dance. It's
It is-
Caucasian.
Kazakhstan. Kazakh.
Kazakh or maybe from Caucasus.
Caucasus, right?
Yeah.
It's like Russian, no, thousands,
Southern.
southern
Southern.
Russia.
nationalities.
And what is the dance, national dance for Russians?
Ballet, maybe. Ballet? Ballet?
Ballet? Yeah, the Russians are good in ballet. And also in music.
Yeah. Classical.
The ballet and music, the Russians are good in these two. Ballet and...
Not in physics. Not
No.
in physics.
Not the physicist. Yo, Alexander the first, Alexander. You disappointed me. Okay, so this is a nice, very nice, strong comment, guys. Very strong comments. And then the curl of H will be B, and the gradient of B is 0. The divergence of B is 0. You know that, right? Yes. The divergence of B. Actually, this all is getting to that answer that I want from the magnetic field. The divergence of the B is 0, so it means that you cannot have monopole. You cannot have monopole. This is supposed to be 0, and it is 0. I believe it's 0. So when someone tells me that you can have a monopole magnet, I can't believe it. I can't accept it. You can engineer that to have something like monopole, but you have engineered that. It's not that it is monopole. You know what I mean? It's like that you make an arrangement that you have only magnetic field comes up from one thing and then closes itself. It's not monopole. It is engineered to behave like a monopole. Okay, I don't believe in monopole, no. But don't tell anybody, okay? This is the Laplacian of B dot, and equal to the value we have replaced it, and would be the Laplacian of B dot, and del to the power 2 of B dot, actually, we say. Good. Now, yeah, for the half space, then we have this. Eventually, we have this. Run 2 of b sub z to run y to the power 2 would be equal to mu sub 0 n e to the power 2 over m b dot. This is general, okay, for even non-conducting ones. B dot, we can assume such a solution for this differential equation, and alpha would be this value, and using the boundary conditions, then we get b dot sub z is equal b dot sub c sub 0 e to the minus alpha y. This is correct for normal conductor or superconductor. Yeah? We didn't differentiate them. It is a general form. So, this is the same. For example, even if this is copper, you still have this. But then you have B dot. Means variation of magnetic field. Then this can happen. Yeah? This is what we had from before. But in superconductor, let me make this point. In superconductor, even for the B, we have this. It doesn't have to be B. Using London equations, we will get there, okay? In normal calculations, you have to have beta, variation of beta. And you know that when you have electromagnetic fields coming to a plate, if it is AC, it doesn't pass through if it is copper, yes? For example, when you don't want anyone knows where you are, you put your mobile, where do you put your mobile? In a pot. You close it. A metal pot. Yeah? When you are in elevator sometimes, you don't have elevator here. When you are in elevator with metal plates, mobile don't work. Why?
The waves are
Reflected?
yeah, reflected by the metal.
Exactly. If the metal is conductive, it has a good conductivity and a good number of ends, then the penetration depth becomes very little, and then the plate is, for example, 1 millimeter, the signal will be mostly reflected back. Okay? And that is the penetration depth for various metals, copper, gold. For example, let me tell you this. Most of the places, even here, we have 50 hertz electromagnetic waves. Yeah? We have 50 hertz electromagnetic waves. Why? Even in this room, we have 50 hertz. Is Russia 50 hertz?
Yes.
Okay. So we have 50 hertz noise, electromagnetic noise. Why? Why do we have it, even in this room? Why do we have electromagnetic waves 50 hertz in this room?
50 hertz, it's related to
The power lines, yes. We have 50 hertz. Why?
the frequency of
Yeah, but why do we have magnetic field here? If I have a sensor for the magnetic field, if I make a coil, just put the coil like this, and then I connect the coil to the oscilloscope. Okay? I can pick up 50 hertz easily.
Why?
Wires, exactly. All these wires, they're carrying current, yes? And not always they're twisted. Sometimes they're just two wires. So if you have two wires, the current is going back and forth. Between the two wires, you create magnetic field, and this magnetic field propagates. Even this cable. Oh, this is loose. Even this cable. Okay? This cable is a 50 hertz power line, and there are two wires like this in these cables, yes? Have you opened them? So they generate magnetic field. And this magnetic field propagates. Magnetic field propagates. And here you have at least something like 300 nanotesla peak values of 50 hertz. And it is everywhere. If you go out of city, far from even this power lines, yeah, then you might get rid of this 50 hertz. Back on my lab, I have pretty good lab. We make sensors, magnetic sensors, like squids, like flux gates. And then when we want to try them, either we have to have a cage with thick copper plates, or for very sensitive measurements, we have to go outside city. And it is very hard to find a place that you don't have these power lines, big power lines, you know? Because whenever they're even 1 kilometer away, still, you get a lot of magnetic fields. You know why? These power lines, high voltage power lines. They are like this. Yeah? And the current, for example, goes like this and comes like this. Yeah? Then there is a big loop. This is, for example, a few hundred meters. The distance is about meter. So you have a loop of 100 meters with a width of 1 meter. And high currents are going through it. It generates a damn strong magnetic field. It propagates the magnetic field, propagates up to kilometers. So it's very difficult to find a place that you don't have 50 hertz magnetic field. Maybe you have to go to the deserts, far from city, far from these guys. But these guys are everywhere. Yes? You cannot get rid of them. So then you have in the lab to have a superconducting case. It's too expensive, very difficult. Then we make cases of copper, boxes of copper. And these boxes of copper, we calculate the penetration depth. And it is all tabulated. For copper, this is well known, the alpha value, the penetration depth. And then the shield that you want to make, when you know the noise level or the magnetic field that you have, and you know that how much you want to decrease it, because if this is thin, it will be decreased this much and then propagates like that. If it is thick enough, yes, you can kill it. But the 50 hertz, for killing it to this level, you need to have plates of a few millimeters of copper. And that's heavy and expensive. So you should know the P sub 0. You should know the maximum B that you are allowed to have on the other side. Then you can calculate the thickness that you need to shield. No matter if it's copper, gold, and so on and so forth. And for superconductor, lambda. Superconductor lambda, the penetration depth. That is what you need to avoid. Okay, good. Now, so we have this n sub s of t, lambda is lambda sub L of t. This is what we had, and we discussed this thing yesterday. We discussed this, that, and A sub c, the critical magnetic field, is also a function of temperature. So we had this yesterday. And here we mentioned that if the kinetic energy of superelectrons at this point, this is what I remind you again, if the current goes high, we say beyond this point, the superconductor will be destroyed. Why? When we have too high current in superconductor, too high current above J sub C, critical value, the superconductor becomes normal. Why?
The velocity of charge
Yes.
makes an energy and breaks
Exactly, kinetic energy. You have 1/2 times mv squared, yes? And that kinetic energy becomes more than the binding energy. Yeah? And then you will, what happens is this energy, which is kinetic energy, goes above to delta, the binding energy. So it breaks. And V is proportional to GA. Yeah, is the velocity of electrons. So it breaks. So, okay, that was the point. And the magnetic field also we discussed. If you have too high magnetic field, superconductor breaks. Because when you have too magnetic field, you have shielding current. If you have too much magnetic field, then you get too much shielding current. And the magnetic field can penetrate. If the magnetic field penetrates, the super electrons cannot keep the same order. You cannot keep the same order. They will be disturbed and superconductivity will be gone. Okay? These things we discussed yesterday with the BCS and the pairing things, and the XC is the coherence length, and this is the equation from the BCS theory. This is from the BCS theory. We had this, and we discussed about the wave function, and all of them will have the same wave function, and the gap to delta. We had that, and then we had these discussions about the heat capacity variation, the latent heat, and this one that you did the homework on it. Now, give me the homework and one person explains. I should collect it. Guys, can you hand it over? Don't forget to put your name, guys. Thank you. And who wants to explain? Thank you. Good. Now, who wants to explain?
I explained it yesterday, so I can do it again.
Okay. Because I think your explanation, I kind of helped it maybe, but I said there are more details into it. So,
Alright.
you want to try again?
I don't think so.
Yeah, try.
No.
I can
Try.
try.
You? Okay.
So when the temperature decreases, there's thermal conductivity.
Let us be come with you. When the temperature decreases, you go here. Yes.
Yes, the superelectrons are created from normal electrons.
Yes.
So the order of the system increases. The system becomes more ordered, and in system there are still normal electrons.
Yes.
So still they have more space to travel through the material because the order is better. So the velocity increases, and that is why we have a slight increment of thermal conductivity.
Exactly. And then again, why it comes down again? Because it doesn't stay up. It goes up and comes down. See?
Because the superelectrons are created more and more, and
Okay.
less normal electrons. So
Excellent. 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 Yesterday, you did not mention the effect or the role of normal electrons. When the transition is passed, you have more orders, you have less normal electrons helping collision. So the collisions becomes less. It's like that you have too crowded room. You have many people, but it's too crowded. So they can't move. Then, for example, half of them are gone. Now they can move. So the mean free path, collision-less path increases. So the conductivity, thermal conductivity due to electrons increases. But then, as you go to lower temperature, now the number of electrons becomes too low themselves. Now they cannot carry that much power or heat because now their number is low. You know, it's not like what? It's like that, for example, we have some balls here and we want to transfer all these balls to the other hall, stand-up hall. And you have 100 people here and they all want to do this. And they're normal electrons, they're not organized. So they block each other. They block each other. They hit each other. There are many people to carry them, but they hit each other. They cannot. Then you decrease them by, for example, 40%. Now these 40%, they can handle more because they don't hit each other. You can transfer balls more from this side to that side. But then you decrease them to 5, 4. Now the numbers are not enough. They have mean free paths, free ways to transfer, but there are not that many. So you are here. So it comes down, and it comes down at the end to the phononic, the lattice. This is the electronic part. Okay, good.
I have a question. If there is electron, there are electrons.
Natalia. Excellent explanation, but excellent. Yes, Dave.
There are electrons with don't contribute to make pairs.
Normal electrons?
No. In this case.
Yeah, normal electrons, as far as they're normal electrons, they're normal electrons. I mean, but their number is like that, these people are normal electrons. And then you take them, you put them into class order, then they become super electrons. Then you have less number of free guys to carry the balls. So it's like that. The number of the people or the number of normal electrons now become less because they become more superconductors. And superconductors cannot do that contribution as normal electrons for the heat transfer. Because super electrons are organized. So they cannot move. Yeah? We can have good analogies. In this analogy, it's like that we put them in rows, some of them. So they are there, but they are in row, they cannot move anymore. The free guys, which means normal electrons, they can take the energy and move and put it to the other side. Yes? Okay, good. Good. Okay, we have this ocean belt effect, and we have perfect magnetism in superconductors. Okay, now. Oh.
Yeah, we're
Good.
around out of time.
Yes. So we can have 20 minutes,
Yes.
Yes.
and I also go have something to eat. See, okay, good. See you in 20 minutes or so. Is good? Is enough?
Yeah.
Okay. Okay.
Да?